If you ask an AI model like ChatGPT a basic question, it's likely to give a reasonable and satisfying response. Current models can even make easy work of more complex prompts, breaking them down into logical steps and drawing on its vast pool of training data to deliver an answer or a plan. But relying on a model's training pool has its limitations. Though vast, a model's training pool is incomplete and generally outdated. The internet is vast and not every data point can make it into a model's training set. There are also private stores of information that are inaccessible as training data. There is always new data being generated, either in the public or private domain, which makes keeping models trained on the latest data nearly impossible. Finally, a company may opt to run an internally developed model locally out of concern for security, which can limit the size and capability of the model. A new paradigm has emerged to remedy these issues. Retrieval Augmented Generation, or RAG, equips an agent with the ability to draw from a content store, allowing it to generate responses from a variety of sources outside its model's training set. By leveraging both retrieval and generation components, RAG combines the strengths of information retrieval systems and generative models. The retrieval component searches a knowledge base, in the form of a database or the internet, to find relevant information based on the input query. This retrieved information is then fed into the generative model, which uses it to produce a response that is informed by up-to-date or domain-specific content. RAG is particularly useful for applications such as domain-specific question answering, where the model needs access to vast amounts of knowledge to provide accurate and contextually relevant answers. It also excels in scenarios where the model must adapt to new information dynamically, such as in customer support, where responses must be informed by the latest product details or policy changes. Overall, RAG enhances the capability of AI agents by enabling them to generate more accurate and contextually aware responses, bridging the gap between static model training and real-world information needs. However, the effectiveness of RAG is inherently tied to the limitations of context window size, which constrains the amount of information a model can process at once. AI models handle data by chunking it down into basic units called tokens. For an LLM, tokens can be phrases, words, morphemes like suffixes, prefixes or roots, characters, or special functional tokens. Image processing models segment their input into regions, while audio and video processing models convert continuous streams into discrete units. In genomics and bioinformatics, DNA sequences are tokenized into nucleotides or k-mers, and proteins are tokenized into amino acid sequences. Time series analysis involves tokenizing sensor, telemetry, or financial data into discrete time intervals for monitoring and forecasting. Context window size is the maximum number of tokens a model can process at a time, and is the limiting factor for the size of input a model can handle. For most models, the context window is fixed, meaning it can't be increased without training a brand new version. A common way developers building agents overcome this limitation is by implementing data storage techniques that enable agents to easily search for relevant information. This allows agents to selectively include only pertinent information in the context window of their models, maximizing how much data can be fit within the window for more effective processing. A vector database stores objects in the form of vectors, or arrays of floating points. Each floating point represents a position along an axis, with the location of an object being represented by dozens or even hundreds of dimensions. An object in a vector database can represent a word, image, video, document, or any other piece of data. There are many vector database tools out there to choose from, like open source offerings such as Milvus or Weaviate, and managed solutions like Pinecone. Tools like pgvector let an agent store embeddings in a relational database like Postgres, allowing enterprise applications to integrate RAG alongside their existing workflows. Vector databases make it easy to conduct a semantic search of their contents. Vectors that are clustered are likely to be similar to each other. Vectors representing objects can be generated by general-purpose language models like GPT or specialized BERT-based models. Vectors created by and for the use of AI models are referred to as embeddings, and are the bread and butter of vector database RAG. A typical RAG pipeline conducts a semantic search of a vector database by transforming a query into embeddings and checking for similar embeddings in the database. Similarity is found using the k-nearest neighbor algorithm to determine the cosine or Euclidean distance between vectors. If a search yields multiple results, they can be ranked based on conceptual relevance. The results of the search and the original query are then fed into an AI model for further processing. In a basic RAG application, the result and query are fed into an LLM to generate a user-friendly response with the requested information. Domain-specific models can enable more complex RAG by utilizing embeddings from specialized inputs. These applications can use tokenized DNA sequences in genomics to capture biological patterns, segmented medical images to identify specific anatomical features, or analyze chunked time series financial data to detect market trends. Agent frameworks like Eidolon and services like Coz have RAG features built in, making implementation a breeze for developers of all skill levels. But if you want to set up a RAG system using a vector database from scratch, the process is straightforward. First, you'll want to choose the vector database you'll be using. I went with pgvector because it's easy to install the Postgres and Python extensions and interfaces like a regular Postgres database. Now that you have a vector database, it's time to fill it with content. To do this, take a text file and break it down into manageable chunks like lines or pages. Pick an embedding model like OpenAI's, generate embeddings for each chunk, and store them in the vector database. If you are using pgvector, you can optionally store information about each chunk like its page or line number. To search the database, generate an embedding from a user query and search the database for similar embeddings. Take the result of the search and the original query and pass it into an LLM like GPT as a prompt to yield a human-readable response. And that's all there is to it. You have successfully created a RAG agent application from scratch. I'll have a repository with the sample project linked down below so you can play with this RAG agent yourself. In summary, retrieval augmented generation allows agents to leverage data outside their model's training set. This is useful for agents with domain-specific knowledge and agents that must adapt to current information. Vector databases let RAG applications search for pertinent data to maximize the amount that can be fit in the model's context window and to provide relevant results. The applications for RAG-enabled agents are vast and varied, ranging from customer support and personalized recommendations to complex fields such as genomics and financial analysis. By integrating up-to-date and contextually relevant information, these agents can deliver more accurate and reliable responses, enhancing their overall effectiveness and adaptability. If you want to get up to speed on AI and agents, make sure to check out my previous video where I covered the basics of Agentic concepts. And if you want to learn more about implementing AI agents in your applications, make sure to follow as I have many more videos coming. That's it for this video. My name is Luis. Thank you for watching.